So in here, you'd have one pair there, and then you'd have two unfilled pairs and one filled pair. The reason for this being is that with your electron pairs, the moving electrons create a magnetic field, and to have a completely stable atom, those fields want to cancel each other out. But that takes a lot of energy, so they will want to, we call this orbital filling, they want to occupy the lowest energy state first. So, did I do that wrong? No.
It's good, it's good.
Yeah. So, on any given energy level, so right now we're just talking about the valence electrons, the electrons that are added to the atom last on the outer shell. Those electrons will start filling up these orbitals. So first is a spherical orbital. So this is, at any given energy level, the lowest energy. And it has exactly one orbital. It's just a spherical cloud around an electron, just kind of like a shell. So when you add an electron, you'll have spin in one way and spin in another, and that determines the magnetic field of your orbital.
If you're taking notes, you can write electron configuration, like a topic right now, what we're talking about.
And then they will be spinning in opposite directions, and the magnetic fields cancel out. Now, beyond that, you have three p orbitals. P, Osman, what do they call it? P? Is it pyramidal?
No, like a dumb shell shape.
Right.
Dumbbell.
So,
Dumbbell, sorry.
P orbital has a dumbbell shape, most closely to what I've drawn here, where it's kind of like that instead of like that. That's like an S, that's a P.
That means
Correct me
that
if I'm
you're-
ever wrong, by the way.
Yeah, no, you're good. That means that, what do we talk about orbitals like in the beginning? So someone give a definition of what an orbital is. Come on, team 1 or team 2. You guys, the team who doesn't get,
I
the
was
team
in
who
the middle
doesn't
of
get 3 points,
explaining that.
doesn't get popcorns. What?
Popcorn.
Yeah.
Yeah.
Okay. Team 1. Hey. All right. And so, all right, cool. That's where your electron goes around. So that means that your electron can go anywhere in this dumbbell shape. That's what the orbital means. And so, like Jack said earlier on, that gives that entire dumbbell shape an electron affinity, so like a negative affinity right there.
Yeah, because most of the time it'll just be randomly inside of that, and that all that randomness kind of spreads out evenly. So this becomes basically, you can treat it as just a region that is negative. You can treat it as like a cloud of negativity that will act as though it were like a negative object.
It's like if you're running around with some sort of like spray can of gas, and you run around fast enough, the whole area has a gas in it, even though it's like dissipating. You know?
Alternately, a different way of thinking of it is if you have like a bright red object on a white background,
Yeah.
and so you take this bright red object and you move it around really fast, then it looks like the whole area is a dim pink. So that's sort of how it works. But all of that pink added together has the same effect as just one bright red object. So moving on to orbitals, why electrons start filling them the way they do is that it's a lot easier for them to occupy orbitals that don't have anything at all in them. They can just jump right in. So your p orbitals, because of the shape of the orbitals, you can fit 3 orbitals in any given energy level, and those 3 orbitals can each contain 2 electrons. So looking at my, I think it was a carbon atom. Someone said that earlier. Yeah, it is a carbon atom. So look, when I start adding electrons, I'll fill this empty one first. And I look, and this one's empty, so I can fill that. And now I have a completely filled carbon atom, in that the s orbital on this outer level is filled completely first. Then I start filling in these.
Jack, there's a Wikipedia reference too.
Thank you. Now let's say I want let's go with oxygen add. So I'm going to add 2 more electrons here. Just kind of ignore these groupings. There we go. So now what's going to happen is I have 8 electrons, right? 6 electrons? I can't count. 8 total, but 6 are on my outermost energy level. Those are my valence electrons, the ones I have available to react. So I keep doing that. Good grief. And now I'm going to add those. So these are completely filled. And that's stable. But now this one wants to add in. And it takes a lot of energy to disrupt that stability, to add in that first electron, because that's going to mess with the magnetic fields that these moving electrons are creating. So you think about it, when you have just 3, they're all the same in the 3 orbitals of your p section of the electron cloud. So those will tend to balance each other out. And it's stable. And by stable, I mean it has a low amount of energy, and it likes to stay that way. But when you start adding electrons, the first one takes a lot of energy to disrupt that stability and poke in another electron, despite the fact that it would balance the charge. So the energy of, the ionization energy, there we go, of putting in that one electron jumps up. As you put in the next one, it gets closer to being more stable. So it doesn't take as much to add this from that as it does to add that from just having those 3. And this ends up being fluorine here. It has 7 out of 8 valence electrons. And when you finally add this last one, it feels so good for that atom to have 8 because it's stable. The S and P energy levels, or S and P orbital types, within that, within those energy levels, are completely filled. It's fully stable. So when you're reacting in a chemical reaction, this is the reason that you have 8 as the ideal valence electron number. And with elements like neon and argon and krypton and radon, they all have their S and P orbitals filled in the outer energy level. So they don't want to react. There is no reason for them to change the amount of electrons they have and their outermost energy level because they are stable. So what happens when you don't have all of them? So this is not stable. What state does it want to tend to? Does it want to stay this way? Think about the definition of unstable. What?
It wants to become stable.
It wants to become stable, right.
It's team 2. Going.
So any given atom will want to become stable. So in principle, this means that it wants to fill all 8 electron spaces that it has available. So when you have an oxygen atom, it has 2 empty slots. And thinking of that differently, it has 2 electrons that it will want to fill an orbital with. So if you have, I'm drawing a Lewis dot diagram here. Who does not know what that is? Everyone knows what a Lewis dot diagram is.
Can someone answer that question?
Awesome.
First person to raise your hand can answer that question for one of their team. Yeah.
I don't know what that is.
Oh, see, he's honest. He doesn't know what Lewis dot.
That's technically a correct answer.
Yeah.
Rishi,
Oh.
you wanted to say something?
Okay, yeah, I was gonna say, isn't it like with how many valence electrons, or I mean, well, not really valence, but it's how many electrons in a sense there are.
Right.
But
It's visually showing in a
Yeah.
simple way the valence electrons that are available.
Yeah, it is.
And what happens is they tend to be grouped in pairs if they are in the same orbital, in pairs together, or expressed singularly otherwise. So what happens with oxygen is you have your S have a pair, and your first P have a pair. Then you have 2 that are open from not being full in that P orbital. And to obtain an orbital that is completely filled, it'll end up sharing an electron orbital with another atom. The dynamics of which I think Osmond's going to talk about later.
Yeah.
So you have 2 oxygen atoms. They each have 2 slots open and 2 electrons to offer that need a pair. So they'll end up forming these bonds where the electrons, instead of orbiting normally around an axis like this, you'll have bonds between the atoms, drawing that much
You want
nicer.
The darker one?
Yeah.
Fair pitch.
Good grief.
Oh.
Markers everywhere. Okay. So you end up having these bonds between atoms. And you'll have them kind of form like that. So it's like these electrons here belong to both. That makes sense to everyone so far? Awesome. Now, once...
Ask some questions.
Yeah. So, with these orbitals here, does that mean an electron's going to be right inside here all the time? No. Okay, point for team two. Whichever team this is. Left team. And why is that?
Because, well, it can be like over there, or like you said, but it's like
Right.
highly unlikely.
How do we
Yeah.
know that it's going to be in that place?
Right.
Um,
For the record, he said that it's highly unlikely, but it could be outside of the area we say
One on
probably.
a roll. That's my point. Guys. Come on, pick it up.
because,
Who can tell me why it doesn't... Say it again? So an electron behaves according to probabilities of where it is. Why does it do that? Why isn't it like a baseball, where I throw a baseball and I see the baseball, and then the baseball is over there, and I can say baseball position there?
Yeah, sure, you can join a team.
Appreciate
You're on a team.
Is it because of the charges that they're being pulled?
Not quite. It's not because of their electric charges. It's because of intrinsically what they are, as opposed to a baseball, or a ruler, or an eraser. Say it again? They do move super fast, but that's more of a fact of us not being able to like see them. It's not a fact. It's not an intrinsic property. So if you recall from the very beginning of my talk, I said electrons are quantum mechanical objects. So what that means is that it acts different from what you think intuitively. So this ruler, I can see there's a ruler right here,
It's an eraser.
and the ruler position is right. That's embarrassing. The eraser position is right here, and it's not moving. So I know both its position and its velocity. But a quantum mechanical object can act both as an object and as a wave. So let's pretend this is an electron, and I can somehow hold an electron in my hand. The electron is not actually sitting here. It's likely that it's sitting here, but intrinsically it could also be here and then jump right back here. And it could also be there and jump right back here. Because I know it's not moving, its position is inherently random. While probabilistically it is in a certain area, it could be anywhere.
So that's why we can't calculate the exact position or the exact speed at which it's moving, so the location or speed. Probably heard this in the Heisenberg uncertainty principle. That kind of jogs your memory a little bit from like freshman bio or something. The way we can calculate the probability is due to the wave function. It's with a psi. I don't know exactly if that's I do that correctly, but yeah. So you don't even know what the wave function is. Just know that it exists, and that's how we calculate probability of where the electron may be. And again, two things: you can't know the position or the velocity at the same time. You can know either or. Thus, you can only predict a certain region in which it can be. You can't predict where it exactly is.
Right,
Okay.
thank you.
That makes sense. And then keyword Heisenberg uncertainty principle.
So does that make sense to everyone? Sort of? Quantum operations are weird.
It doesn't make sense. It's okay because it doesn't make sense to most of us.
Yeah, there are like
Or to
I think
real
12
physicists.
people in the world who it makes sense to.
Yeah. So if you think it makes sense to you, you're either lying or you really don't understand it.
makes perfect sense.
So moving on, there are more orbitals than just S and P. There's more complex shapes that you can have. So the next layer is d orbitals. And they have 5 for a total of 10, 5 orbitals for a total of 10 electrons to be held.
And they look really weird. Jeff.
Yeah.
Don't bother drawing. They're just gonna confuse them.
Don't they look kind of like
Like
Anyway.
It's
that?
3D, so it's,
they're a little
Isn't it?
complicated.